Greetings, everyone. I hope everyone's doing well. I hope you all had a great weekend. This is a recording to finish talking about chapter five. We began talking about the importance of the Z-score, and it's important that we continue on the understanding and the foundational principles that we learned. One of the first things that we talked about is the Z-score being a standard measure that allows us to understand where our individual score is located on a distribution. And so what we're going to do is we're going to take our individual score and we're going to standardize it. And by standardizing our score, we're able to put it and level the playing field for every score on the distribution. And then we compare our particular score to other scores that also lie on the distribution. We know specifically where our score falls in relation to our mean, which is going to oftentimes be the center of the distribution or the kind of the most representative value for the distribution. So if our z-score is positive, it's going to lie above uh, the mean. That means it's greater than the mean. Even if your z-score is negative, that means that your score lies beneath or below the average. And that's on the left-hand side of the distribution. So knowing the z-score tells you a lot about where your score is, and it helps you to be able to compare yourself to others. We had an example where I asked you to calculate your z-score for your shoe size or shoe size. So you were able to understand, if I wore a 9.5 and the average um, shoe size for a female was 8, then I knew that I fell above the average, and my z-score would indicate that. Okay, so here are some practice problems that I walk through, and what I'm going to do is I'm going to talk you through the answers for these problems, and then if you have any other questions, please email me. Keys again stop through office hours. But as we walk through these problems, I mean they're not simple, but once you have the understanding of what a z-score is, what the equation is, then it's very, very easy to understand how to calculate a z-score and or be able to try to change or turn a z-score into an actual score given the information that you're providing. Okay. So one of the first questions that you were asked for practice problem one was, it says a score of 75 is measured in a population mean of 100. It says a z-score of z equals positive 1.50 is calculated. Without knowing the standard deviation, explain why the z-score of z equals 1.50 is incorrect. Okay, so looking at this example, you would want to think, oh, am I going to be able to calculate the z-score given this information that we provided? However, I want you to understand that even if you try to, one of the first things that we know about z-scores is the sign of the z-score, whether it's going to be negative or positive. Any z-score where your score is below the mean is going to be negative. Any z-score where your actual score is above the average of the mean is going to be positive. In this particular example, if we're looking at the actual score, looking at the actual score, it looks like the actual score is 75 and our average is 100, right? So it says that we have a z-score of positive 150 or 1.50. It will be impossible because, again, our x or our score is less than our mean. And if our score is less than our mean, our z-score should be negative. Okay, so it says explain why the z-score of positive 1.50 is incorrect because your value for your score is less than your actual mean. And so since that's the case, we know that we have a negative z-score and a positive z-score. So without having to calculate the standard deviation, you would already know that this is incorrect because this z-score should be negative and not positive. Okay, so if you were to look at the distribution. Okay, so I'm going to draw this out. So if this is our normal curve, okay, we have our mean here. We have our mean, which is 100. Okay. Our x value is going to fall somewhere in here because it's going to be x equals 75, right? So x equals 75. Okay. So anything that lies in this region to the left, that's going to be a negative z-score. So this should be a negative z-score. I'm not sure why it's doing that. My apologies. I'm going to try one more time. If it doesn't work, just take my word for it. Okay, negative z. Okay, anything to the right of the mean is going to be a positive z. Okay, okay, so that should be a positive z. All right, so anything going to the left would be negative. Anything going to the right would be positive of that mean. Okay. So again, that's one rule to remember as you are again looking at what your z-score is, how it should correspond to your actual score. Okay. So that is the first problem. Okay. That's how you would explain it. Again, in this particular example, your mean is greater than your actual score. So if that's the case, then your z-score should be a negative z-score, positive z-score. Okay. So again, x is less than mean 100, so the z-score must be negative. All right, practice problem 2, okay? So it says identify the letters in the following distribution that correspond to the following z-scores. So again, using your knowledge of z-scores, the values of each z-score and where they fall in the distribution. For a z-score, the z-score will have a z of 0. So this would be the middle of that distribution. It's going to be 0. Anything to the right will be positive. 1, 2, 3, anything to the right. And then anything to the left will be negative. Of course, we remember that. All right. So if we're looking at 1, okay, z for a positive 2, we would automatically know that since this is a positive number, it's going to be the only one that's positive. It's going to be out here in the D, right? So that should be positive 2 out here, okay? It says z equals 0. Again, C would be the only one that is a 0, so the 0 should be here. It says -2 and -0.50. So we know that negative z-score is going to the left of that the 0 value here. So this should be the closest to the 0 should be -5.50, and then this A should be -2.00. Okay. So again, those are again very, very easy, but knowing where each z-score is in relation to this center or the mean of your distribution is really important. So if your actual score is in the middle of the distribution or equals your mean, it's going to be 0. So your z-score would be 0 in this particular case. All right. So again, just be mindful of that as you think about identifying the letters in the distribution, like being able to locate the values is important, and that lets me know you understand where scores are located in the distribution. Okay, anything out here to the right would be again positive, so from 0 out into infinity, and anything to the left would be 0 out into negative. Okay. All right. So for this one, self-explanatory, but uh, they're giving you your mean and they're giving you your standard deviation, and they're asking that you would find the z-score for each of the following x values. I'm going to only do this for one. Okay, so once you do it for one, you should be able to do it for each of them. All right. So, and actually, what I'm going to do is I am going to use my whiteboard because I don't feel like drawing on this. So this would be a little easier for me. Second, let me get, and I actually might, I'll do the first two, and then I'll let you all have done the rest, okay? And then I'll show you the answers. All right, let me go to my whiteboard here. Okay. All right. So here's the whiteboard. So they gave us values of for the population with a mean of 50 and a standard deviation of 6. Okay. So what we're going to do is our first one was x equals 50. We know that our z-score formula is this, x minus our mean over our standard deviation. Okay. So for this example, for the first one, we have z equals 50 minus the mean, which is 50, over our standard deviation, which is 6. Okay. 50 minus 50 is 0 over 6. 0 divided by 6 equals 0. So the first z-score should be 0. Okay. Let's do the second. Okay. The second one was x equals 62. Okay. So if it's x equals 62, then I'm going to go z equals 62 minus 50 over 6. Okay. 62 divided by 50 is 12. 12 divided by 6 is 2. Okay. I'll actually do the other one so we'll be able to see it. Let me go to my problem, the last one. Okay. So that is 53. So the x equals 53. Z equals 53 minus 50 over 6. So this should be 3 over 6. This would be 0.5. Okay. And since we have some that are, so that's their last one, let me go down. Let me do one that's a negative z-score. So we got x equals 44. So that'll be z equals 44 minus 50 over 6. Okay. This should be 44 minus 50 would give me a negative 6 over 6. Negative 6 divided by 6 should give you a negative 1. So a z-score of negative. Okay. And since I'm already almost there, let's go ahead and finish it off. We got x, so 47. Okay. So that'll be z, 47 minus 50 over 6. This should be negative 3 over 6. That'll be a negative 0.5. And to finish it off, x equals 38. Z equals 38 minus 50 over 6. This should be a negative 12 over 6. That gives you a negative 2. Okay. So you have all of them. First one, you should have 0. Second one, 2. Third one should be 0.5. Your fourth one should be negative 1. The other should be negative 0.5. And the last one should be a negative 2. All right. Let me stop sharing. Go back to my slides. Okay. And so there are your examples there. Okay. 0, 2.5, negative 1, negative 0.5, negative 2. All right. Here is another example, but instead of for this example problem, you're going to be changing your x value, your z-scores into your x values, given the same population and the same standard deviation. Okay. So let's go back to our problems. I'm going to do the first two, and then I'll allow you to do. Actually, let me do one of the negative ones, and I will do a positive. So I'll do positive 1, and I will do a negative 1.50. Okay. So I'm going to do this one, and then I'll do this one. Okay, let me share my screen, my whiteboard. Okay. All right. So again, we have our same mean, 50. Our standard deviation is 60, or 6, excuse me. Our first z-score was +1. And then our second one was, I'll go here down, -1.50. All right. So given all that information, right, we have our z-score, we have everything, we find our x value. So what I'm going to do is, I'm going to just, again, we know my formula for our z-score is x minus my mean over my standard deviation. And I'm going to be solving for my x value. So knowing that, I'm going to go ahead and solve for it. Before I do it, actually, let me do it this way. Okay. So this should be x equals our mean plus z times standard deviation. Okay. So all I'm going to do is I'm going to plug those numbers in. I know my x. So that's going to be 50 plus 1 times 6. So again, x equals 50 plus 6. X equals 56. That's the first one. Okay. So given, again, this information right here, given that information, I can solve for the last one, right? But for this last one, instead of it being a positive here, instead of it being positive right here, I'm going to turn that into a negative because it's a negative z-score. So that should be minus, boom, okay? So if we go down, this one should be x should be equals 50 minus 1.50 times 6, okay? So I'm just going to do the math here. Doing the math, you got 1.50 times 6. That's going to give you 9. So this would be 50 minus 9, x, 50 minus 9 should be 41. Okay, so you got 41 there, and you got 56 here. Okay, so I did a positive one, I did a negative one. Again, having a positive z-score and having a negative z-score just changes these values here. But again, you're going to be using either that for a negative z-score, and you'll be using that equation for a positive z-score. Up so you can see that. Again, you'll be using this one for a positive z-score, and you'll be using this one for a negative z-score if you're trying to find your x value. Okay. All right. Let's go back to the slides. Okay. So given all that information, all right. So again, for number one, for this first one, 56. For the -1.5, should be 41. And again, if you do these for all of them, again, it's going to be very simple given the equation that I provided to you. Again, and I'll write it here so you can see it again. So you would have your x equals your mean plus or minus your z times your standard deviation. That's the equation to find the x value that corresponds to your z-scores. All right. All righty. So we'll go ahead and move on. But again, that is going to be, again, how you solve for your x values corresponding to those scores. Okay. And if you have any questions, please rewind, go over again, practice, practice, practice these. If you can do these in your sleep, you should be perfectly fine. Just knowing the relation from which you go from an actual z-score defining the z-score, or when you have to turn a z-score into an actual score given your mean and your standard deviation. Again, knowing the relationship between all of those variables is important, like we talked about in last class. If you can do that, you're going to be great. All right. So let's move right along. Okay. Standardizing a distribution. Okay. So many of us, if not all of us, has taken a standardized test. Okay. And a standardized test is called a standardized test because what they've done is when they give you a score on this standardized test, they have taken your individual score and they have made it a standard score. And what I mean by that is when they standardize your score, they're putting your score in the midst of everyone else's score, but everyone else's score has been standardized. And if everybody's score has been standardized, then you can compare your score to anybody's score in the world, right? So if everybody's taking the same ACT test, may not be the same questions, but we know that's a standardized test, or an SAT test, or a GRE, or an LSAT. All of these tests are standardized. And when they're standardized, that means you're taking a individual score, you're standardizing, you're putting them on the same plane. And as you do that, then you're able to compare your score with everyone else's score. So you'll understand when you get a mean, you get a standard deviation for a particular standardized score, or say you have an IQ test. An IQ test is a standard score. The IQ test has a mean of 100 and has a standard deviation of 15. Okay, so you will know if you score a 100 on an IQ test or have IQ of 100, you know you hit right at the mean or the average. If you have a 115 IQ, that means you're one standard deviation above mean, and you are significantly, so you're 60, maybe 68% at 68 percentile, right? So that means you scored 68% or higher than 68% of individuals who take IQ. Okay. So again, those types of standardized scores allow us to understand where we lie on the distribution. And it's very, very easy to standardize because all you're doing is, and for our example, is you're taking your actual score and every score in the distribution, you're turning every score into a z-score. And we know for a z-score has a specific mean and it has each of our standard deviations. So one standard deviation, two standard deviations, three standard deviations. Standard score, standard distribution. And we know that every distribution for a z-score has a mean of z. And we'll talk about that. Okay. So when you use z-scores to standardize a distribution, all you're doing is, again, transforming all of your x values into z-scores. And we know how to transfer values into z-scores. We are and should be pros at that, given the examples that we've done, practice problems that we've done in class. Okay. So it says the characteristics of a z-score transformation. Every z-score distribution has exactly the same shape as the original distribution scores, right? There's no difference. So if if an actual score of distributions has a normal distribution, when you transform all of those individual x values into a z-score or z distribution, it will also have a normal distribution, okay? A mean of z-score distribution or a mean of a z-score will always be zero. Okay, that's one important note to write down right away. Okay, it will always, and when I say always, it will always have a mean of zero. Always have a mean of zero. So this is always true. Okay, this is always true. And a distribution for z-scores will always have a standard deviation of 1. Those are two distinct things that you should always know. Okay, the mean will always have a mean of 0 for a z distribution and a standard deviation of 1. And a z-score distribution is called a standardized distribution. Why? Because we're able to turn these individual x values into a standard measure that we can turn any distribution into a z-score distribution, meaning again value of 0 for the mean and a standard deviation of 1. And when we do that, that makes it that much easier to compare scores across distribution. Okay. So here is an example. Okay. For this example, we have our X values. This is population of scores for our X values. Okay. So in order to transform these values into Z scores, you have a zero, you have a mean of 100, you have a standard deviation of 10. In order to change these values here into values Z values, all you're doing is doing the Z score distribution, doing that Z score formula. You're going to use that score again, has a mean of 0 and standard deviation of 1. Okay, that is always going to be true. And again, you can do that for any value in a distribution. It should give you something very, very similar to what you see. Okay. So this is again, scores, all population of scores for your X values. This is the population of Z scores. And again, these distributions are exactly the same. All right. But again, always has a mean of 0 for a Z score, always has a standard deviation of always, always, always. Okay. There are not many times where you hear always, but when you hear it, make sure that you take note. Okay. So again, for your x-axis, all you're doing is you're taking your standard deviation. Okay, so for in our example, in the previous example, we had a mean of 0 and a standard deviation of 10. Okay, so every distribution, every standard deviation increases by 10 points. So in this particular example, one standard deviation above the mean is 110. Two standard deviations above the mean would be 120. Three standard deviations above the mean would be 130. So if we went out here, this would be 130, okay? Because of how each standard deviation is just, again, 10, okay? Again, we transform our actual score to a Z-score. Let's do this really quickly, all right? So if I'm churning this 100, say my actual score is 100, okay? So if my actual score, my X value is 100, okay? I hate that it does that. Let's do this really quickly. Actually, I'm going to go to my whiteboard because this is kind of aggravating. All right, so let me go to my whiteboard really quick and I'll draw this out for us so I can show you, re-illustrate this. Okay, let's go to my whiteboard quick. All right, so here's our whiteboard. So we're gonna go, I'm gonna draw this out again for us. All right, so this is my mean. It's a mean of 100. That's one standard deviation, two standard deviation. That's negative one standard deviation, two standard deviations, right? So if we increase in again, we have our mean of 100, we have a standard deviation of 10, okay? So given this information, we know that this should be 110, this should be 120. If it's 10 standard deviations, again, standard deviation of 10, one standard deviation below the mean would be 90, and two standard deviations below the mean would be 8, okay? And again, we go down here. We know if this is my mean, this is going to be 0. And I know this is 0 because if I scored a value of, let's say, 100, and I want to get the Z score for a value of 100, Z equals 100 for my X value, again, because this is my Z score formula, okay? So it'll be 100 minus 100 divided by 10. 100 minus 100 is 0 over 10. 0 divided by 10 is 0. That is 0 right there, okay? One standard deviation over, that should be 1. This will be 2. This will be negative 1. This would be 2, -2. I'm going to show you, again, if I went, again, 2 standard deviations above the mean, right? We would go z equals, and again, I'm using the 120. 120 divided by 100, or minus 100, excuse me, divided by 10. So this would be 120 minus 100 should be 20 over 10 will give you 2. Again, corresponds to 2. Let's go 80. Z, 80 minus 100 over 10. 80 minus 100 gives me -20 over 10. -20 divided by 10 should give you -2. Again, that's there, that's there, okay? So all of those things, again, we're transforming our X values into Z-scores, and this is, it should always be true. You're gonna have, again, a mean of 0 and a standard deviation, and it corresponds, okay? So if you're transforming your X values, always look like this, okay? So if you go down, these are your values for the 120, 2 standard deviations above the mean, and this is 80, that's -2 standard deviations below the mean, all right? Okay, let's go back to my slides. Okay. Here we go. Okay. So it says using Z-scores for making comparisons. And that's one of the main reasons why we use Z-scores for anything that we do, especially when we have scores that are in different distributions. Okay. All Z-scores are comparable to each other. Why? Because every Z-score is a standard score. And every Z-score distribution has a mean of 0 and a standard deviation of 1. So if I know that, I can have a Z-score for any distribution, and I will know where my distribution, where my actual score lies in that distribution based on the Z-score that I'm given, okay? And whatever Z-score corresponds to my X value, it lets me know where I lie in the distribution, right? So if we're talking about, again, if I know that my Z-score for my IQ, okay, let me go here and see if it works. So if I know IQ has a mean of mean of 100, and it has a standard deviation of 15, I know that when I turn it into a Z-score, again with a mean of a mean of 0 and a standard deviation of 1, I know that if I get a 115 or score a 115 on an IQ test, then I'm going to lie, again, 1 standard deviation above the mean. Because again, 1 standard deviation above the mean, Z equals 1 is also going to equal X is also going to equal, sorry, it's not doing how I want it to do. It's also going to equal, it equals 115. Okay, so getting a 115 on my IQ score will also, again, be equivalent to me getting a Z-score. Okay, so if you want to calculate the Z-score, go forward. 115 minus 100 gives you 15. 15 divided by 15 gives you a Z-score of 1. All right, go ahead and erase this. Okay. So it says Z-scores allow the direct comparison of scores from 2 different distributions because they have been converted to the same scale. And again, that's essentially what we're doing because again, we always have a mean of 0 and a standard deviation of 1 for a Z distribution. Again, we're converting the scores to the same scale. And I'll show you an example here next on how we do that. Okay. So it says Dave received a score of 60 on a psychology exam and a score of X equals 56 on a biology test. It says, for which course should Dave expect the better grade? Suppose the biology scores, I have a mean of 48 and a standard deviation of 4, and the psychology scores had a 50 and a standard deviation of 10. Okay. So in this example, we know that Dave has scored above the mean on both exams. Okay, so we know that he scored a 60 on a psychology test where he had a mean of 50 or an average of 50. He scored a 56 on an exam where the average was 48. So he scored above average exams. But which exam did he score better, right? And so we're going to figure that out. Okay, so given this information, let me go to my whiteboard real quick. And so I'm going to show you how you would do this. Because again, what we're going to do is we're going to convert each of these scores, the 60 and the 56, we're going to convert them into the same score, same scale, which is going to be a z-score. If we convert them to the same scale, we'll be able to compare them because we know that, again, z-score has to be 0 and standard deviation. Right? So let's go ahead. Let me go to our whiteboard. Okay. So again, given the information I know, all right. So for my psychology test, I'm going to go ahead and write out everything for psychology. Okay. So psychology, he got a score of 60, and the average for that exam was a 50, and the standard deviation was 10. Okay. So we automatically know that this exam had it's pretty variable, a big variance. Okay. For biology, okay, he scored a 56. And that exam had an average of 48 and a standard deviation of 4. All right, given both of these, right? Given both of what we see here, I'm gonna go ahead and write out to the side. We got to find our z-score. Again, remember that our z-score formula is going to be x minus our mean over standard deviation. Okay. Given all this information, I know what I'm going to do. So I got my z. I got 60 minus 50 over 10. 60 minus 50 is 10. 10 over 10 is 1. Okay. Got my z-score for my first exam, my psychology exam. Now, what's the z-score for the biology test? It'd be 56, 48, or minus 48 over 4. So we got 56 minus 48. Okay, 56 minus 48 should be 8 over 4. 8 over 4, 8 divided by 4 is 2. Okay, so given the information that we've been provided, okay, scored a 60. The average score for that exam was 50, but a standard deviation of 10, meaning that there was a lot of variance in that exam. People scored all over the place, right? However, for the biology test, the standard deviation was 4, so there wasn't as much variance as it was in the psychology test. He actually scored a lot higher in comparison to everyone else in the exam. So he scored 2 standard deviations above the mean. In the biology test, he only scored 1 standard deviation above the mean for the psychology test. That means that he did way better on the biology test than he did on the psychology test in comparison, because what we did was we converted the actual values, even though they had the different means and different standard deviations, we converted them to the same scale. And when you convert them to the same scale, then you can compare them to one another. So again, a z-score of 2 versus a z-score of 1 means the z-score of 2 is better than 1. So he scored higher and is doing better in the biology test or biology class than he's doing in the psychology class. Okay. All right. But again, the key to that example was we had to convert them to the same scale. Once you convert them to the same scale, then you are able to compare them, right? Again, if you have any questions, go back and look at that example again. You can rewind it, look at that example. But again, converted those two tests, two values to the same scale. Once you do that, you have um, you have an opportunity to compare them to one another. All right. Okay. So it says other standardized distributions based on z-scores, right? So again, you create a new distribution that has simple values for a mean and a standard deviation. So again, oftentimes it's easier to create a distribution that is simply just whole numbers, right? So when you're standardizing a distribution, it's very, very easy to, again, create a more basic scale that's easier to compare values, right? The SAT test, the ACT test, the IQ, they're all standardized measures, okay? And they have standardized scales. And more often than not, all you're going to do is you're going to transform your original scores and you're going to transform them into z-scores, right? So again, it just happens in two steps, right? You take your z-scores that you transformed into from that you turned into z-scores, and you transform those z-scores into new x values. So that your specific mean that you want and your specific standard deviation that you want are attained. Okay, so I'm going to show you what that looks like on the next slide. Take you through an example. So say we had an example where our mean was yeah, let's say our mean for our original scores was 38 and our standard deviation was 4. But I really want my mean to be 50 and my standard deviation 10. All I would need to do is I would need to turn my, again, transform my z-score into, or those original scores into z-scores. And then I would transform those z-scores into the values that I want them to be. And I'll show you what that looks like. Because what you're going to have to do is you have to find the x value that corresponds to the z-score for your new distribution. And I'll show you what that looks like. Okay. So here's what I mean. Okay. So you have your original scores here. Okay? You have your original scores here. These original scores have a value of 57 and a standard deviation of 14. Okay. I want my standardized scores to have a mean of 50 and a standard deviation of 10. Okay. So what do? First thing I'm going to do is I'm going to find the z-scores for these actual scores, right? I want to transform these scores into these, okay? Very, very simple, very, very easy to do, okay? And once you do it, everything else is going to fall into place, all right? So if we want to transform Maria's score, she got a score of 64 on the original score, and we want to transform that to the standardized score, okay? All right, let's do this really, really quickly. So for our, go ahead and do this on the screen here. So for our original distribution here, 64. Okay, Z formula, 64 minus 57 over 14 equals 7 over 14 gives you 0.5. Yep, 0.50. Okay, let's Joe's score. X equals 43. Z equals 43 minus 57 over 14. This would be negative 14 over 14 equals negative 1. All right, given this information, right? Given this information, I know that these are the z-scores for my original distribution. So again, I'm using these scores and I want to transform them and standardize them to my original distribution, right? So all I want to do is take these z-scores and I use them to find the values for my standardized scores, okay? So you're going to take this 0.5, okay? I know that I'm looking for my x value, okay? I know my mean, which is 50. I know I have a standard deviation of 10, okay? So what I'm going to do, I'm going to multiply both sides by the 10. That cancels, that cancels. This is multiplied by 10. That should be 5, okay? X minus 50. I'm going to add 550 to both sides. Plus 50. So X should be 55 and is 55, okay? Checks out, okay? Again, I changed this original score, which was 64. I wanted to transform it into standardized distribution of a mean 50 and a standard deviation of 10. All right. I want to do the same thing for Joe. Okay, I'm gonna do Joe's down here. Okay. I know he has a z-score of -1. Okay. I know everything that I need. So that's x value here. I know that's 50 over 10. Okay. I don't need to put the equals from there just yet. So multiply both sides by 10. Just the algebra of it all. Okay, so this should be -10 equals, again, let me not skip. Those cross out, so this should be x minus 50. Okay, all I'm gonna do is add 50 to both sides. Running out of screen here. Add 50 to both sides. Okay. Jack that up. Add 50. And after you do that, that cancels. X equals 40. Okay. So our new scores now lie here. This is where Joe sits at 40, and Maria sits in here somewhere. She's about at a half distribution or a half standard deviation, so she's about right here. This is Maria. Yep, she sits right here at 55. Okay. So again, that's how you create a standardized distribution. If you want to standardize your distribution, again, the steps are very, very simple. You have to find the z-score that corresponds, because again, if we know our z-score is a standard score, right? So if I want to create a standard score, all I'm having to do then now is create the x value that I want to find with that standardized score, right? I have to create, if I want it to be equal, even numbers, right? So this is 57, mean of 57. Let me get my pointer. The original distribution had a mean of 57 and a standard deviation of 14, right? I want the numbers to be very, very basic and rounded off, right? So I changed the mean to 50 and the standard deviation to 10. I could do that. And I can do that because all I need to know now is what is what are those standard measures, right? So I got these standard measures, zero point 0.5 and negative zero point 0.1. And once I have that information, I can use the z-score formula to now locate X value, okay? Very, very simple. Once you understand the process, you will likely be asked to do this on an exam. So understand what the process is, how you transform scores from one score to the standardized score that you want, given the information that you provide. Okay. I am going to, I'll just keep this again, rewind if you need to. Um, but again, very, very complex, but not so complex once you understand how the relationship is between all of your values that you're giving for your z-score function. Okay. All right. This one says a population with a mean of 90 and a standard deviation of 20 is transformed into z-score. After the transformation, what is the mean for the population of the z-scores? Okay. Again, think about the rules for a z-score distribution. Again, it was an always, right? You had two statements that were always going to be the case. Okay. So for this particular example, you should have gotten C. Okay. Because when you transform your scores to z-scores, your z-scores will always have to be 0 and a standard deviation of 1. Okay. So a sample with a mean of 70 and a standard deviation of 15 is being transformed into z-scores. After the transformation, what is the standard deviation for the sample of z-scores? Again, every z-score distribution is going to have a mean of 0 and a standard deviation of, the answer should be 1. Okay? Always, 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 these are trick questions. This will always be the case. Again, remember that, put those in your notes for safekeeping. All right. It says a score of 59 comes from a distribution with a mean of 63 and a standard deviation of 8. It says this distribution is standardized to a new distribution with a mean of 50 and a standard deviation of 10. What is the new value of the original score? I'm going to give you some time to look this one over, but I want to solve this one out for you so that you can, again, see, again, how it's worked out again, okay? I'll give you some time. Actually, let me go ahead and work it out. Pause the video. I want you to work it out for yourself. And then I'm going to show you on a separate screen how you get this solved, okay? Let's do it. I'm going to take it to the whiteboard. Take this to the white. All right. So again, your original score. You got x equals 59. And that comes from a distribution where the mean is 63 and the standard deviation is 8. All right. We know that our standardized distribution okay, it has a mean of 50 and a standard deviation of 10. Okay. Given that information, the first step in order to turn this value, this 59, into a standard score on that new distribution, that new standardized distribution, I have to find my z-score. That's the first step. So the first step is going to be to find the z-score. So my z-score, again, the formula is going to be your x value minus your mean over your standard deviation. Okay, meaning I'm going to just plug my numbers in. My x value for this one's going to be 59 over 63, or minus 63, excuse me, divided by 8. Okay, this one should be negative 4 over 8. Negative 4 divided by 8 should be negative 1/2, or negative half, excuse me. Negative 0.5. Okay. Boom. Given that information, now I can make some moves. All right. So I know my z-score for my standardized distribution. I mean, for my original score is going to be negative 0.5. So negative 0.5. I don't know my x value, but I do know my mean, and I do know, but again, I'm looking for the value that's going to correspond in this new standardized distribution. Again, remember, I'm just going to use this formula because I know that's how you find your x value. Okay, so I got x equals, my mean is 50 minus 0.5 times 10. All right, so this should be x equals 50 minus 5. Okay, x equals, go down a little bit so you can see my work, 45. Okay, so if we go back, that should be the answer. Okay? That should be the answer. And I'll go back and let you see. Okay? But again, that is how you would work that out. Okay, so let's go back. Stop sharing here. Go back and share here. All right, so again, you have original score, 59. It comes from a distribution with a mean of 63 and a standard deviation of 8. The distribution is standardized into a new distribution where the mean is 50 and the standard deviation of 10. Again, what is the new value of the score? Again, we found that the z-score for this distribution, for this x value, was a negative half. We found that our actual x value for this new distribution is going to be 45, given that our z-score is negative half. Okay, so we should have gotten, again, 45, just like we did. Okay. All right, learning check. It says, which of the following is an advantage of transforming x values into z-scores? Okay. A, all negative numbers are eliminated. B, the distribution is transformed to a normal shape. C, all scores are moved closer to the mean. D, dissimilar distributions can be compared. Again, we talked about being able to compare, okay? One of the reasons why we turn anything into a z-score, any distribution into a z-score, is so that if we have distributions that are not very similar, we can use the distribution to put them and place them on the equal or level playing field. And so the reason we do that is because we want to be able to compare. So your answer should be D, okay? Making or comparing dissimilar distributions. That's one of the main reasons why. Okay. All right, to look ahead. All right, so as we move forward, okay, especially when we talk about inferential statistics. Inferential statistics, again, we're going to be using samples to answer questions about population. So we're going to take, say we have a population of 100,000 people, okay? And we want to understand, let's say 100,000 students, and we want to understand the level of self-esteem in 100,000 students that attend HBCUs, okay? So I have this population of 100,000 students. And then what I want to do is I want to administer a survey to 1,000 students. You know, I want to see if those 1,000 students have what their self-esteem score is. I know that if I have that 1,000 students, that's going to be pretty representative of students in the HBCU community. Right. So I take that sample and I look to see what the mean is for that group of 1,000 students. Right. I can use that group of 1,000 students, that mean, that self-esteem score, and then be able to generalize that score to individuals in the general population of HBCU students. right? So the interpretation of our research results really depends on the sample. Is our sample noticeably different from the population, or is it the same? So sometimes what we want to see is the self-esteem score, is it any different than it would be on average in the original population, right? And so sometimes you want to compare, right? Maybe you have two groups of individuals. You have one group that attends an HBCU, and you're looking at, you know, the self-esteem scores for students that attend HBCUs, and then maybe you're comparing that to all students in the nation of the United States, right? And so now we're comparing HBCU students to the entire population of students in the U.S., right? And so is there a difference? Is there a noticeable difference in HBCU students' self-esteem versus those the self-esteem students across the country? Right? We could be able to determine what that is, right? And we're able to do that because of called inferential statistics, right? So again, we're taking um, information that we get from our samples to answer questions about populations. That's the idea. And again, as we move forward, it'll make much more sense. Right now, we've kind of been working with populations, but as we begin to use samples more often, you'll get an idea of how we use and why we use samples to be able to, again, draw inferences about populations that we want to study. Okay. So again, here is an example. Okay. So you have the original treatment, excuse me, original population. This is a population that has not been treated for anything, right? And so what they do is they take a sample of those individuals out, right? So this population has 100,000 people, um, and maybe I want to treat them for depression. Okay, so they have 100,000 people with depression in a particular area. This is my original population. I pull out a sample of 100 individuals. Okay, I give those 100 individuals a treatment, and maybe it's psychotherapy, maybe it's a sort of medication, but it's a treatment. Maybe it's a treatment for 1 month. I then measure the treated sample and I measure the original population and their depression scores. And I want to see if the treated sample is any different than the original population. Did that psychotherapy, did that medication, did it help with depression or not? And I want to be able to see what those differences are between those populations. That's one of the major things that we're going to be doing in this class, right? As a researcher, you're going to be unable to kind of study the entire population. So pulling out a sample makes it a little more feasible, makes it a little more, uh, it makes it a little easier. And those individuals are a little more accessible than the entire population is. So then you can make that inference to the entire population. So now you know if the treated population, if their depression levels are lower, or incidences of depression or their mood has improved, then you know that that drug, that psychotherapy, whatever that intervention is, does work on the population. And so then you would want to treat the entire population with that intervention. Okay. So again, here's just an example of you think about distribution, right? Being able to look at where you lie on distribution is really, really important, right? So you have a population of non-treated rats, right? Then you have a group of treated rats, right? These individuals out here, right? So this is treated rats, and it says this is the distribution of weights for adult rats, right? So you got the mean is 400. This might be 400 grams, right? So you got that's 20 standard deviation. So your standard deviation of 20. So 420 is one standard deviation. 440 is two standard deviations above the mean. You have two distinct scores. You got 418 and you got 450. Now 450, that's a very, very rare weight, right? 418 falls within one standard deviation of the population, right? So that doesn't look as, um, that doesn't look as extreme, right? So when you're looking at a population, now you're able to compare your weight to somebody else's weight because now you place them on a, a Z score, on a Z distribution. And now, again, you convert it to the same scale. And now you can see how you can compare weights. You can compare uh, heights, whatever the value, whatever the variable is, but you can compare them because you each convert to the same scale. Okay. So here's a learning check. It says last week, Andy had exams in chemistry and in Spanish. On the chemistry exam, the mean was 30. On the standard deviation of 5, and Andy had a score of 45. So on the Spanish exam, the mean was 60 with a standard deviation of 6. And Andy had a score of 65. For which grade or which class should Andy expect the better grade? Okay. So I'm going to tell you right off the bat. Okay. You should not have to do any work. Okay. You should be able to look at these and kind of eyeball the and how these work. Right. So he scored a 45 on his Spanish exam, or excuse me, on his chemistry exam. Okay. He has a mean of 30 and a standard deviation of 5. Right. So I automatically know that his score is greater than the average. Right. It's greater than average. And I already know that it lies at least 3 standard deviations above me. I see that automatically because the standard deviation is 5. He has a value of 45. 1 standard deviation above the mean would be 35. 2 standard deviations above the mean would be 40. And 3 standard deviations above the mean would be 45. Right? So I can draw it out for you so you can see it. As a matter of fact, I will draw it so you can see it. So for chemistry, this is what it would look like. Sorry for the uneven line. Draw this out for you so you can see it. Sorry for the janky distribution there, but this is the mean here. That's going to be 30. Actually, I'm going to draw it on. Let me do it on my whiteboard. Yep, let me do it on my whiteboard so you can see it. Let's do it on the whiteboard. Out of here. Let's do this. But again, you shouldn't have to really do anything. All you gotta do is look at your values, right? So it says in chemistry, let's go to Chem. He scored 45. Me was 30. Standard deviation is 5. Spanish exam, Espanol. He scored 65. Mean was 60. And standard deviation was 5. Or excuse me, 6. So again, with the Chem, I know this is the mean of 30. Standard deviation of 5. Okay. So if you want to go ahead and do it, you can do the Z-score. It's going to be 45 minus 30 over 5. This should give you 15 over 5, 3. Okay. That's for Chem. For Spanish, Z, I'm going 60, 65, excuse me, minus 60 over 6. This should be 5 over 6. And given this information, you already know and can see that this is going to be way less than 3. So 5 divided by 6 gives you 0.833 repeating. Okay. So here is this information here. Right. So 3 standard deviations above the mean, that's very, very high. He has less than a standard deviation above the mean. Right. So 0.83 is a little bit less than 1 standard deviation above the mean. He's doing a lot better in his Chem class than he is on his Spanish. Okay. So again, not even having done that, right? You should be able to look at the standard deviations and be able to determine just off the bat that he's doing better in chemistry because of the standard deviations, right? And where they lie on the distribution. All right. Yeah, so chemistry should have been it. True or false? It says transforming an entire distribution of scores into z-scores will not change the shape of the distribution. Okay, think about that one. Then it says if a sample of n equals 10 scores is transformed into z-scores, there will be 5 positive z-scores and 5 negative z-scores. Okay, think about those two. Okay, but for the first one, it says transforming an entire distribution of scores into z-scores will not change the shape of the distribution. The shape of the distribution will remain the same, right? We're just again converting those z scores, right? And then it says if a sample of n equals 10 scores is transformed into z scores, it'll be 5 positive, 5 negative. We don't have enough information for that to determine. All the 10 scores could be located above the mean. They could be located below the mean, right? So we don't really know uh, where those scores lie on the distribution. So it doesn't really give us enough information to determine. Okay, so the first one should be false. Should be true, and then the second should be false. Okay, all right. So again, first one, location of the score relative to all of the scores is unchanged. So the shape of the distribution is unchanged. Nothing will change. Just converting those z scores, excuse me, those actual scores to z scores. And then the second one again is false. The number of z scores below and above the mean will be exactly the same as the number of the original scores above and below the mean. Okay, so we don't know where they lie. It didn't give us enough information to determine where they lie in the distribution. All right, that's all we got for chapter 5. Again, a lot of great information. I hope that, again, go back, rewind, uh, work through some of those problems, work through, again, especially the practice problems. Know how to convert an X value into Z-score, learn how to convert the Z-score to an X value, know how to standardize a score. Okay, go back, rewind. Uh, I will have office hours this week. But again, let me know if you need anything. But again, this is a foundational principle. Okay, it's the foundational principle. Being able to convert um, an actual score into a standard score is really important. I hope that you got a lot out of this lecture today. Continue to practice the skills so that you get a lot better at everything that we're doing in class. Again, it's going to get a little more complex, but with a solid foundation, I know you will do extremely well. So keep going. I'm proud of each of you and sticking and hanging in there. And I will see you all soon. You all take care.